We can wait for 1 or 2 minutes because the numbers are people are joining in. So
okay. So let's wait for 2 minutes.
Sure. Maybe in the meantime, I can ask you how are things going there? Did everyone, like, do people go for lunch together? And
Oh, this is in distributed mode, so
for you as well. Okay, but the students are together, right? Like
some of them.
Some of them. Okay.
Yes. This is kind of hybrid mode conference. So
Yeah.
excuse me, I think we can start. It's already 3.
Yes, it's important to be on time, and we have to other talks also. So I would like to welcome everyone who has joined this session, and also the speaker Nitika Shakwardhe, and it's my pleasure to introduce her. So she did her master's from IIT Kanpur, and subsequently she did her PhD with Professor Lucian Hardy from University of Waterloo on an operational road towards understanding causal indefinites with post-quantum theories. And causality is perhaps the most fundamental rule which governs everything, means apart from minimum energy configuration, everything obeys causality. And so her research interest in that sense is foundational quantum mechanics or quantum foundation, and of course the related aspects of quantum information and communication. And at present, she is a postdoctoral fellow in International Center for Theory of Quantum Technologies at University of Gdansk, Poland. And today she will talk about her works with many aspects of applications of causality will appear in that, but the specific title of her talk is how models of indefinite causality can be understood within the causaloid framework. So I'll not take more time. I'll request Nitika to share her slides and start the talk.
Thank you so much for the lovely introduction. Let me just make sure that the share screen is working. So let me know if you can see the screen.
Okay, it's coming. Now it's visible.
Now it's good? Okay. So, yeah. So, okay. The only thing is, if you can give me a warning of maybe when 15 minutes are remaining. That would be really nice.
Sure.
And I mean, we have a slot for 1 hour, but I would like to, like, if anyone has questions, please feel free to ask, maybe put them in the chat or and ask questions. And I would like to keep some time in the end as well, if people want to have a short discussion. Okay, great. So I think I was going to tell a little bit about myself, but that was already done really well. So yes, I did my master's long ago in IIT Kanpur, and it was really nice to see some speakers at QIQT, like Anand sir and Vandre sir, also speaking at this remote conference. And now I'm going to talk about mostly works based on my PhD thesis, specifically chapters 4 to 6, and also ongoing work that is offshooted from this. And okay, so essentially, I want to talk to you about what the causal light framework is. And to motivate it, we'll talk about indefinite causality and what that means. But you have seen some talks about this in this QIQT workshop already previously. Fabio Costa gave a talk this week. So you saw the process matrices. So these things are in the same area of physics. And let me motivate what we even mean by indefinite causality. So there is a paper by Lucien Hardy back in the early 2000s. It's called, as you can see, the title is Probability Theories with Dynamic Causal Structures, a New Framework for Quantum Gravity. And really, the essence of what he was trying to say in this paper, the motivation was really trying to understand the radical aspects of general relativity. So general relativity is in a way deterministic, but it has dynamic causal structure, and you need to define, let's say, the state on a hyper-Cauchy surface to figure out what happens before and after, to define the causal relations between different events. On the other hand, in quantum theory, we have a fixed causal structure. If you look at quantum circuits, there's some state, and irrespective of what the state is, the order of events that are in its future, like the gates that will be applied, cannot be controlled by the state. So there's a notion of a fixed causal structure, which means that the order of events are fixed. But on the other hand, in quantum theory, the radical aspect we want to focus on is its probabilistic nature. And really, if we want to go towards some framework of quantum gravity, it would require necessarily to marry these radical aspects of both these theories, dynamic causal structures and probabilisticness. And one could actually go further and think that the probabilisticness can actually make the causal structure itself indefinite. And that is what we really mean by indefinite causal structure. And then following this paper, so this is the paper where the causal light framework was introduced. And following this, there has been a lot of research in this field, including the process matrices, as well as quantum combs, and more frameworks. There's just a vast literature out there. But most of them focus on the beginning of the literature focuses on trying to study this from a post-quantum lens, which means that you have Hilbert spaces, and you can think of quantum combs as the supermaps over CPTP channels. So something that takes a channel and gives you a new channel back. And therefore, you have to assume that the wires correspond to quantum systems. But on the other hand, there is a different literature which pertains to the reconstruction of quantum theory, and also in the early 2000s, which was kickstarted by this paper, Reasonable 5 Axioms for Quantum Theory. And what is done there is that you want to talk about a landscape a landscape of theories, logically possible theories within which quantum theory lies, by identifying some principles. And given these principles, you want to identify what principles govern quantum theory without assuming necessarily Hilbert space structure and so on. And the approach in the causal-light framework is similar, but it goes beyond GPTs. So this landscape can be called the generalized probability theories. So you only assume some preparation, transformations, and measurements, and you assume that you get probabilities back that are real and positive and between 0 and 1. So now here you can think of the causal-light framework as a landscape of theories which have GPTs that also allow for indefinite causal structure. And now we can discuss how it was actually formulated. So part of my thesis was finding diagrammatics for the causal-light framework, so a diagrammatic language to understand it. And I'll be using these diagrammatics in this talk. The next thing we did was we tried to, so once you have a landscape of theories, you want to categorize them and understand them in some manner. And we do it with respect to a hierarchy we introduce, which I'll talk about. So I'm just giving a short outline. And then finally, at the end of the day, we want to understand where things we already know fall within this framework. So I will give you two concrete examples. And when I say concrete, it's still quite abstract, but the set of DO tensors. So a DO tensor is a framework which are a class of generalized probability theories, which have some rules like local tomography obeyed. And we show that these fall within this hierarchy in a certain way. We also, so this is on the side of GPTs. From the other side, we show how the process matrices, an example of indefinite causal structure, fall within the causal-light framework. And then I will end with some open questions. So now I will spend some time trying to explain what the causal-light framework is. So the story goes as such. You can imagine a person in a box, and without loss of generality, it can be Lucian. And now this person really, what they have is they are inside this box. They do not have access to anything outside in the world, but they want to understand the underlying theories in this world. And the way they do it is by they get a stack of data, and they have this data which is in the form of cards, and each card contains some information. So what is the information contained on this card? It has some location, some actions. You can think of it as the settings of an experiment, and some observations. So given some settings, what happens, right? So you can think of it, you can think of it in many ways, but a location can be something relational, saying that I am next to this person, and this person is next to someone. It could also be much more concrete, like GPS coordinates, right? And actions and observations can also depend on what you have. And now really you can think of these actions providing you procedures and these observations giving you outcomes. And now this person is given with this stack of cards with all logically possible events happening in the world that can happen in the world are in these cards. And they need to organize this. They need to reduce this set of cards to the minimum possible to still be able to predict the probabilities for events happening in the world. This is the goal. And how do they do that? So they start by organizing the cards first into, if some set of cards have the same location, they'll make it into one stack. And you can think of that as a set. So you can think of it as a set, an elementary region. We use the word elementary if you cannot fine-grain further this location. So you cannot further figure out. So a non-elementary region would be where you say anything within this room is considered a region, but an elementary region would be literally just every entry of this particular location being in a stack. Good. And then you can find subsets of, given a region, you can find subsets that have some procedure F. So this is literally having some procedure in this region, and these are sets, so you get a new set. And the third set you get is given some region procedure, what outcomes you see. And then of course you can deduce that YRI would be a subset of FRI, which would be a subset of RI. And now we're interested in these probabilities. So here this Y is the outcome. So we are interested in the conditional probabilities of the outcome in some region, given the procedure in that region, of course, but also the outcomes and procedures anywhere else. And once we have this, we say that at least at an operational level, we are done. And then one can spend more time understanding the ontology of the theory, but that would be an undertaking for a later time. And really the story of this person in a box forces the person to employ this operational methodology. Good. So now we have this. So we now have this stack of cards, and one can go back to the stack of cards and calculate probabilities just in a frequentist method by just saying, what is the size of this procedure set versus the region, what is the size of this outcome set versus the region, and so on. Like one can do that. And therefore you have these probabilities. We'll start with these joint probabilities because one can always go back to conditional probabilities at a later stage. So now you can think of this as joint probabilities. What are these wires? So each of these wires correspond to a different elementary region, and the alphas correspond to indices for the number of the cards. So now the number of the cards can be really large. And the number of the cards can be really large, which means that alpha belongs to a really, so, okay, just to put this in perspective, you can think of a Stern-Gerlach experiment. So your procedure is, let's say, just the angle at which you're sending the system. And now, because these cards contain all logically possible settings, you would have, in principle, an infinite number of settings. So these alphas are really these labels. And now we can actually try to write this in a generalized bond rule as some inner product between a measurement and state. But notice that when we talk about states and measurements in ordinary quantum theory, we have a notion that the measurement comes after the state. And we've already have this implicit notion of causality between them. So we have to go to a generalized notion of measurement and state. And the way you do it really is to say that the state is something the region cannot control. So it's basically something that's prepared by the rest of the regions. And the measurement is literally the procedures as well as the outcomes that you can do that give you these labels, these alphas. So now we are really interested in this measurement R over these multiple regions. And going forward, so yes, I missed one thing here. So now, as I said, these alphas are correspond to really big sets, indices in big sets, but the point is that any physical theory correlates this operational data. So if there's any correlations, any physical theory that's not completely arbitrary, then you will have these correlations, and you want to use these correlations to compress your sets, therefore your cards, and we call this physical compression. So this is not the compression you see in like channel compression or like encoding decoding schemes. This is the physical compression you get from considering many possibilities and the structure, the mathematical structure that underlies these correlations. So in the causalite framework, there are 3 levels of compression. The first 2 are provided here now, the tomographic and compositional. So you can think of tomographic compression literally on a single region such that you find a fiducial set that will be able, so you choose a fiducial set, you know what happens for these fiducial set events, and from this set, you can do a convex combination over these entries to get any other probability for another setting. And therefore, now you might go from some sets that were really big, these gammas, to omega sets. And now, because you do this tomographic compression on each region, you have a Cartesian product between the sets. So these labels L1, L2 belong to omega 1, omega 2, and so on. And therefore, this tuple belongs to this Cartesian product. And maybe a bit about the physicality of what tomographic compression means is this is something you already know, you already use. When we talk about a qubit, we don't write down the state with infinite entries, we do it with a few. We know we need only 4 real numbers to express a qubit if you do not assume normalization. But on the other hand, for a classical bit without normalization, you need 2. So actually, the tomographic compression also differentiates different theories like classical theory, quantum theory, and PR boxes, for example. And so this is things we kind of know already. And then one can ask, what is the next level? So now you already did tomographic compression on each region, but what if you had done tomographic compression on all these regions together? Would these be different? Of course. And this difference is captured in this compositional compression, which takes regional tomographically compressed entries, and basically it captures what are the causal correlations between these regions. So a priori, when you started with these regions, you had this data and you had no idea how these regions are causally related to each other. And if you have some non-trivial compositional compression, then you would know that there is some causal relation. So if you actually start with a system that are all spatially separated, then the compositional compression will be trivial. But on the other hand, if you have time-like separated events, but actually not just time-like separated, but more so causally adjacent, such that only regions that really are causally adjacent can influence each other's correlations completely. And that's captured here. And now we have this new indices K1 to Kn. And this belongs to this omega set 1 to n, which is a strict subset if you have non-trivial compression of this Cartesian product. Good. So now we have done 2 levels of compression. We are almost halfway through the talk. And now we can define the 2 major implications of the causal-light framework. So now you can define what is the causal-light. The causal-light is this lambda, this bold lambda, and it's literally just a set of all these elementary region, the tomographic compression over elementary regions. So these lambda matrices. So these are represented by boxes, but these are basically taking, these are matrices that are rectangular, which go alpha times L. So they are rectangular, and they basically have they compress the information from all your observed data. Further, you can also list all the compositional compression over non-elementary regions, and just the set itself is the causal-light. And the reason it's called the causal-light is because if you are given this object, then in principle, you can calculate all probabilities for any event in all these regions. And therefore, you can calculate the conditional probabilities, which we were interested in. And therefore, at an operational level, the causal-light prescribes the theory itself. And then you can have something called the causal-light product. And the motivation for the causal-light product is to have a causally neutral product. So in quantum theory, we have 2 kinds of product. We have sequential and parallel composition. So when we have parallel composition, we use the tensor product. If we have sequential composition, we multiply these matrices, right? So if we want to talk about indefinite causality, we need to necessarily be able to not make these demarcations unless required a priori. So the causalite product basically captures how regions are correlated with respect to each other. Either this can reduce to the tensor product, this can reduce to sequential composition, or something more general. And therefore, you only need in this framework a single product, and you don't have to define sequential and compositional products separately. Good. So now we talked about two levels of compression. There's one more left, which is called meta compression. And we will define meta compression and then define a hierarchy over it. So now I can basically write the causalite again, but in a different form. So here what I'm saying is we have, we listed, so assume you have n regions and some finite number of n regions. Then you start with the tomographic compression here. And then you have compositional compression over 2 elementary regions, compositional compression over 3, and so on. And this is just rewriting what we had before, but in a more categorized way. And now you can define a hierarchy. And okay, so before we define the hierarchy, meta compression essentially would mean that there is some compression over the causalite itself, meaning that you may not always require all these lambda matrices. So in physics, we have these concepts of isotropy or some transformation invariant physics, and really that should be captured. And we need not always need the compositional compression of everything. And therefore, what you can do is say that in principle, you can restrict the set given some rules of how to get back. So for example, if you can compress, if you want to do meta compression and remove these, then all you have to do is just have the set and a set of rules of how to get this lambda matrix back. And this is actually how we define this hierarchy. We cut it off. We cut off this the elements in the causalite until d regions for some d less than n, where n is the total number of regions. And we define some rules such that you can get a lambda on or lambda o d prime back, where d prime is more than d. And if you can find such rules, then you would say that in this hierarchy, this theory obeys and falls under lambda OD sufficiency. Okay. And now the rest of the talk really is trying to understand what this hierarchy means. Okay. So the first thing is you can have D equals to 1, which means that you cut off all compositional compression. You just cut it off here. But that would mean that once you're done with tomographic compression of elementary regions, you're done. And that would mean that in this physical theory, there are no causal connections at all. And this is something we are not interested in studying. So it's a trivial theory that we don't want to study because there's nothing interesting going on. There's no notion of causality. Then you can go to the next level, the next rung, and you can say we cut it off at lambda O2, and then any compositional lambda matrix of lambda O3, O4, and so on should be expressible as some function of lambda O1 and lambda O2s. And this is what we studied in detail, and we show that these two frameworks I was talking about, the duotensors and the bipartite process matrices, actually fall into this rung. And now we will go through some details to substantiate this claim. Okay, so let's take a very simple example. Let's take n equals to 3. So this is the spherical cow version of what we're trying to do here. And then you can write down your causalite. Just as you can enumerate all the lambda matrices. So you have tomographic compression between region 1, 2, 3. compositional compression between 1 and 2, 2 and 3, 1 and 3. So pairwise compositional compression, and then you have 3-region compositional compression. Okay. Now you can ask if you want lambda O2 sufficiency, which means that this lambda matrix should be expressible as some form of all the preceding ones. Then if lambda O2 sufficiency holds, then this diagrammatic equality can hold. And one can also write down the symbolic form. So, but for the sake of the talk, I'm trying to give you a more intuitive picture of how these things work. But again, feel free to ask questions. Good. So what's happening here? We have tomographic compression and we have lambda O3 applied here. And then we say if it's equal to tomographic compression and then pairwise compositional compression of 1, 2, 2, 3, and 1, 3. Notice that this wire is just passing through this. So this lambda matrix is still a pairwise lambda, a compositional compression matrix. Good. And if this holds, then now you can try to characterize these equations. So let's consider an even simpler case where region 1 and 2 are causally adjacent and 2 and 3 are causally adjacent, but 1 and 3 are not. So you can think of this in quantum theory as a circuit where you have gate 1, 2, 3, and then because 2 is in the middle of 1 and 3, then the correlations between 1 and 3 can be destroyed depending on what 2 is. So therefore 1 and 3 are not causally adjacent. They are causally related, but not causally adjacent. And then the earlier equality reduces to this, which symbolically you can write down. And the reason you want to write this down is to basically be able to specify the compositional compression omega set. So we said that lambda 1, 2, 3 was a subset of lambda 1, Cartesian producted with lambda 2, Cartesian producted with lambda 3. But here we find a form for what it looks like given these causally adjacent relations. So you can think of it as like, you can think of these Ks as these labels. So you can plot the L1 indices on one axis and like L2 on another and L3 on another, and you can try to see how these intersections work. And pictorially, then K would lie in this black space. And note that, so to get to this equation, you need some intuitions, and these kind of intuitions are based on how to, so we are used to thinking of theories with also omega sets that can be Cartesian producted, which I will mention again for quantum theory. For quantum theory, this holds. So you can look at this inequality, and actually we are interested in characterizing this, even though we know cases of this, but this is not the most general case. So here you can think of these as different wires are independent, so their indices are independent, something like that. Okay. Okay, so now I just want you to remember this slide. We will keep coming back to it, but what in the slide? This image, and this image corresponding to these lambda matrix relations and these omega set relations. And therefore, going forward in some framework, if we are able to write this framework in terms of the causaloid objects, if we can define the generalized measurement, generalized state, if it's written in an operational manner, then we can try to parse it and see if it obeys these conditions. And if it does, then we know that it falls in this hierarchy in this particular way. And even though we take the specific case, in principle, one could consider all kinds of causal relations between these three regions and find the subsequent notations. One more important comment I'll make at the expense of being pedantic is that here some of you should ask me now that, well, you know, you have this lambda matrix applied first and this one second. What if you had it the other way? So in principle, you can do this. You can apply it the other way, and then the form of this equation changes slightly. Nonetheless, the structure of this omega set stays the same. As you can see, it is symmetric in 1 and 3, and it doesn't capture the order of these lambda matrices, even though here you do because you're summing over things. Okay, good. So now we will apply the causal-like framework to two things. So this is part 1 and part 2. So the part 1 would be to the DO tensors, which I'll mention again what they mean. And then the second part would be to these bipartite process matrices, which you saw in Fabio's talk sometime this week. So let's start with the DO tensors. So the DO tensors, I'm aware that maybe not everyone is familiar with them, and that's completely fine. But you can think of the DO tensors as this diagram here. It's this diagram where you have different ways to combine fragments. You can think of this as A, B, C as some operations, H as some operation, and then you join these fragments such that if you don't have any wires left open, it corresponds to some probability of some event. And now it looks awfully similar to what a quantum comb is, because this ABC looks like a quantum circuit, and this H looks like a quantum comb because it takes these channels and gives you a probability back. But here you're not assuming a Hilbert space structure. Here you actually have a generalized probability theory underlying this. So therefore, the DO tensors are a class, a subset of generalized probability theories that follow certain rules. And one of the rules is called local tomography. And what that loosely means is that these wires A, B, and C are independent, meaning that irrespective of what is sent over B, if you wanted to do tomography of A, all you needed to do was tomography of these wires A, B, and C, and you didn't need any measurements on B, C together to characterize the tomography, to do the tomography of the operation. And once you have these assumptions in there, you can use them to show something, and which we will do now. So above we have the causal-like framework equality we talked about. And now what we are going to do is we are trying to write down the probabilities associated with the DO tensor and massage the equation in a very explicit form. Now you can see that I've just opened these labels, and there are these white and black dots, which are part of the DO tensors. It is attributed to the word duo of the DO tensors because they are like tensors, but they have different types of wires, and there are rules of how they compose. And all of that is maybe outside the scope of this talk, but if someone wants to talk to me about DO tensors, I'll be happy to later. But one can now rewrite this here. The only thing happening from this step to this step is we've added these 3 circuits. And this circuit, this loop with these 2 triangles, this is a circuit which has probability 1. So you can just put them in there. And now you can compare this drawing to this drawing to identify the lambda matrices of the DO tensors in the causal-like framework. And once you do that, you find that you can write down the lambda matrix. This lambda matrix is the compositional compression of 3 regions. And then you have the compositional compression matrices of 2 regions pairwise. And now we said that for lambda O2 sufficiency, you want to be able to write this in terms of these 2. So now in the DO tensors, that is asking if this can be written in terms of these. And it is possible precisely because of local tomography, that you can write these wires separately. And once you have that, you can actually show that any lambda O3 matrix can be written in terms of tomographic compression and these elements in the DO tensors, which correspond to elements of 2-region compositional compression only. And therefore, at the end of the day, what you've shown through this is that the DO tensors fall on the second rung of the hierarchy we defined with respect to meta compression, which is a reminder of which is here. Okay, so a whole class of GPTs we know of fall within the second rung. So now let's ask another question of what about indefinite causal structure, models of indefinite causal structure we know. So the most popular one, the one that has been most studied in the literature is the process matrices. So let's take a bipartite process matrix. We ask the same question. So on the top, you have the same thing from before, the causal-like framework relation that is required to be satisfied if you want to show that something falls in the second rung of the hierarchy we defined earlier. And now let's go to a process matrix. So process matrix is, so here you have A and B. A and B correspond to some CPTP maps with some input and output Hilbert spaces. And a process matrix is a bilinear map on these CPTP channels that gives you a probability back. And so it's also defined using this Choi-Jamil-Koski isomorphism and writing the Choi states for them. Nonetheless, for us, what is pertinent is that we will associate. So for the causal-like framework, we need to associate regions. And we'll do that. We'll assign A to be a region, B to be a region, and the process matrix W. I mean, I think I wrote P here, but most people use W. So let's stick to W. And then you can write down the omega sets and the lambda matrices. So here we are showing the omega sets for A, B, the process matrix W. And now you want to also be able to write down the omega set for the compositional compression of A and B. But without W, A and B cannot be compressed. They are just independent. So there is no compositional compression here, meaning that A and B are these regions 1 and 3 that are not causally adjacent. But on the other hand, when you compose the process matrix with A, you get a different process matrix back that can take one channel and give you a probability. So it becomes a comb in a way. And so this you can specify, you can do the same for BW when you compose B and W. But when you compose ABW, you get probability back. There are no indices anymore, and it's a single a set with a single element. And now if you carefully go through the lambda matrix calculation, you can actually see that these conditions above that we have written down are also satisfied by bipartite process matrices. And now, okay, so what have we learned? So let's try to see this schematically of this categorization of this landscape of logically possible theories done through an operational manner in the causal-like framework. So we have two competing hierarchies. The first one I didn't mention because it's not new till now, but now it's pertinent to mention it. So it has to do with the tomographic compression. So I touched on it briefly when I said that for a qubit, you need 4 real numbers, and for a classical bit, you need 2 real numbers to specify the state without normalization. And actually, you can write this down in a very particular way by asking the number of real numbers you need to specify a state in some GPT, and the number of distinguishable states, perfectly distinguishable states. And then you get some parameter R, and the values of R change for different theory. So for classical theory, it's 1, but for quantum theory, it's 2. So one use, like in the reconstruction of quantum theory, people use this to be able to differentiate classical and quantum from a principled approach, as opposed to other ways. And now what we have shown is that, so this is one compression axis. The other one corresponds to this hierarchy we have introduced with respect to compositional compression. So we had this lambda OD sufficiency for various Ds. So here the parameter spaces are, and here it's D. And for D equals to 1, we didn't really care about this, as I said. For D equals to 2, we have shown that the duo tensors, which, so the classical probability theory and So classical probability theory and quantum theory are special cases within the duotensors. So when we show that the duotensors fall in this rung by, we have also shown that classical probability theory and quantum theory also fall in this rung. And then we also, so this, the work with bipartite process matrices is ongoing work with Natalia Moller. And here we are showing that it also falls in this rung. So what does this really mean? What do we learn from this? How do we go from this point? And ideally, it would have been interesting to be able to differentiate indefinite causal structure phenomena in this hierarchy, but it seems like everything we know falls there, at least. And I mean, there are other things we need to check, of course. But this could mean that, well, maybe we don't really need to care about the rest of the space. So if you think of the causal framework as a scaffolding which gives you a landscape of theories, and you need some principles to constrain it to be able to get some finite version of quantum gravity within it, then this could be one of those principles which says that, okay, let's restrict ourselves to lambda O2 sufficiency. But this is just, I'm just telling this as a direction in which we can go in, but this is not something we have concretely done yet.
So Nitika, means about 10 minutes for the main talk, and then we can take a couple of questions.
Great. Okay. No, so I just have, I think maybe 2 slides more, which is just the outlook. So
Okay,
that's great.
fine. Yeah. So 11 of them.
Yeah. Good. So I was just talking about this directions. So one was that we can think of this as a restriction to this space and use this to study, use this as a principle to disregard the rest of the space. And the other thing one can do is actually try to construct a toy theory that falls in some lambda O3 sufficiency. And one way to do that, which is a project which we haven't finished yet, but it's trying to construct the trio tensors analogous to duotensors, using the same mechanisms, but generalizing it. And I think this is my last slide. I should have had a thank you slide. I don't, but I am thankful. But this is the last slide to give you just a roadmap for what we're trying to deal with. Here we have quantum theory. When you operationalize it, you work more with quantum information. And then to go towards post-quantum theories, one space is GPTs, as I mentioned, and the other is indefinite causal structures. And really both of these go back to the causal-like framework, within which we expect that an operational version of quantum gravity should be sitting as a point in this landscape. So that's where I'll end. Maybe I'll keep the slides up, and depending on what questions we have, and if not, then I'll stop the sharing as well. So thank you for having me, and please ask me any questions you have.
So the floor is open for questions. Means I can see there are more than 60 participants. So I hope there will be many questions. You can unmute yourself and ask questions. If you have any question, just unmute yourself and ask questions. Or alternatively, if your mic is not working or from some other reason, you can write in the chat box also.
Usually if someone's typing, it takes some time to be formulated. But I would encourage people to ask questions, even if you're shy or if you think the question is not well formulated, it's fine. This is the right forum for it, I think. And of course, like, feel free to write to me if you have questions as well.
Can I ask a question?
Yes, please.
Yes, thank you for your talk. What is the full form of CPT? Completely positive theory or what?
So CPTP maps that I was talking about?
Yes.
So completely positive trace preserving maps. So
Okay.
in quantum theory, you have unitaries, but a more general form are CPTP maps.
It means the density matrix should have positive eigenvalues, right?
It just means
This
that
is
it's a
what
map
you.
that can take a valid density matrix to a valid
Yeah.
density matrix, as opposed to a unitary which takes you from pure states to pure states and stuff like
Yeah.
that.
So diagonal element should be more than equal to 0.
Yeah, yeah. I mean, it's yeah. So
Are you going to consider nonlinear interactions also, or because here, if I understood correctly, you are considering only linear interactions?
so uh, so when you assume an operational framework, you have this requirement that you get probabilities back. And when you assume this, you need some linear structure because probabilities themselves have this linear structure embedded in them. So when people study these generalized probability theories, they are quite general, except that at the end you want a probability that's real, that's coming back, and these probabilities should add to 1. And that actually gives you this linearity requirement. So that's why we assume this. Yeah.
Okay, thank you.
Any other question?
Excuse me. Hello.
Please continue.
Yes, we can hear you.
Yeah. This is not a question. This is a request. Can you suggest few papers regarding this, like maybe in the chat, so that we can get like for beginners like us, it's really difficult.
Yeah,
So yeah,
but what kind of things you want to learn about, like this causal framework or more
the
indefinite
GPT part, the
The
GPT
GPT,
part,
yeah.
GPT, and as well as the causality framework. Yeah, thank you.
Okay. So I think like I can do this right away, but is it possible that I send like an email to the organizers and they can somehow forward this information to students?
Yeah, sure, no problem.
Yes, that can be done.
Yeah, so I'll do this. I'll collate it into a document and I'll just send it to the organizers and hopefully they'll pass it along.
So, means in your structure, where you place the other theories, means which has a general structure like generalized local theories or generalized no signaling theories.
So if you're talking about no signaling like Bell correlations, is that what you mean? Or
Yes, means.
So you can study Bell correlations within GPTs because I mean you must have seen this very famous
Signaling
diagram.
is means that just you are adding that means faster than light communication is not allowed. So signaling is not allowed, and then there are general structure of theories which allows everything else. Means correlations is not limited, but signaling is not
Exactly. Yeah. So that falls within the purview of generalized probability theories already, because you know this diagram with if you see the Bell inequalities, but in this non-local game version as opposed to the CHSH version, then you show that there the bounds are 0.75 for classical, and then the Searleson bound is 0.85. And then for the logical one, you have these PR boxes. But these PR boxes are an example of generalized probability theories. So there, what you do is you, as you said, like you have this principle of no signaling, which you can impose. But you're working with subsystems, and these subsystems are general, and they can be written as GPTs. Yeah.
So is there any other question? So especially for students, means even if you are for some reasons you are not asking questions at the moment, if you want to drop a mail, you can also drop a mail to a speaker.
Yes, please. Like feel free to, and I think maybe my email should be available, but maybe I'll also write my email in the chat.
Yeah, that makes sense. You can write your mail and that.
Instead of people trying to look for it, I'm giving my Gmail because it's something that's more permanent than university emails, and
Sure.
I just prefer it this way. So, and maybe in the next
talk, thanks for addressing students' query in the mail and everything. Yes. And now we'd like to thank the speaker once again and for a beautiful talk. and
Thank you.
move to. So we can see the next speaker is already logged in, and it's a continual session. So though we are running a bit early because the next talk was scheduled at 4, but I mean, we can always start, and that will give us opportunity to ask more questions at the end of or for more discussion. So it's my pleasure to introduce the next speaker for the plenary talk. So Professor Yaron Bromberg is our next speaker who will deliver a plenary talk for the conference, and he's an associate professor at the Racha Institute of Physics. He went to a postdoctoral fellowship at Harvard Medical School, followed by another postdoctoral fellowship at Yale University between 2012 to 14. He received his PhD in physics at the lab of Professor Yaron Silberberg at the Weizmann Institute of Physics, which is very famous. He is an experimental physicist who studies quantum optics and other related topics, and his work investigates what happens to photons, the fundamental particles of light is made of, and when they are sent through the opaque materials. So it's a very easy to visualize situation that you have a semi-transparent or opaque materials, and you are sending light through that, but at the quantum level, what happens there? And so definitely we are not looking for something which happens in day-to-day life, where we live in the classical world. So as our expectations, the talk will be towards the non-classical nature of light, and specifically the topic is non-classical light in complex media and its application. So I will not extend the introduction anymore. I would like to invite Professor Yaron Bromberg to share his slides. And sorry if I pronounce any of the name of the institute or your surname a bit incorrectly. So I would like to request Professor Yaron to deliver his talk and share his screen.
Thank you very much for the kind introduction. And can you all hear me and see my slides?
Yes, it's perfectly visible.
Okay, excellent. So thanks again for the kind invitation. I'm very happy to be part of this distributed conference. I liked a lot the idea, and I'm happy I can take part of it. So as you mentioned, I'm an experimentalist in quantum optics, and we work a lot on sending photons through opaque and scattering medium. And I want to give you a little bit of flavor of what we do and other labs in our field are doing. So I gave it quite a broad title, Non-Classical Light in Complex Medium. And actually this talk is based on a recent review paper Oad Lib and I recently wrote. So if you're interested in hearing more details, please take a look at this review. So let me see. Yes. So maybe I should say a few words. What do I mean by complex medium? So basically, any type of medium that light can propagate through and can propagate in many different directions, many different paths. For me, it's a complex medium. So it could be a scattering medium like a cloud. A cloud eventually is made out of transparent drops of water, but altogether they result in multiple scattering. Has a lot of interesting physics there. It could be biological tissue. It could be nanophotonic waveguides. And it could be multimode optical fiber. So a fiber with a large core can support multiple modes, and there are many different paths the light can go through. And all this brings about, first of all, a lot of important and interesting applications like imaging through tissue and optical communication through fibers, but also a lot of fundamental questions on how light behaves at the fundamental level, at the quantum level, when it goes through these kinds of systems. So I want to start really with the basics. Before we talk about the quantum light and photons, let's for a second think how a classical particle scatters. So think of this ball falling on this scattering medium. You can think of just pegs that the ball hit, and every time it hits a peg, it can go either to the right or to the left. This is sometimes called a Galton board, and you can collect the balls in the downstream and just do the experiment again and again and again, throw the balls many times, and check where it ends up. So naturally, most of the balls will fall under the position we started with, but there'll be a distribution, there'll be a spread, because there are many different paths the balls can take, and sometimes it could get hit more to the right than to the left. And at the end, we see some Gaussian distribution, and in fact, one can describe this process with a diffusion equation. So this is the classical particle, very, very intuitive. In quantum mechanics, we know that there's a superposition. And in fact, when a ball falls or scatters like this, one has to take into account all the path it can go through the sample and add them coherently. We need to take into account the superposition of all the different paths, and then take the absolute value squared, look at the probability. And this can result, this interference, this superposition can result in interference effect. So it might be that all the path that leads the ball to this cell over here will interfere destructively, so it will never hit there. And on other places, we'll have constructive interference, so that we'll have a higher probability to get to one cell and not to the other. And overall, we don't see some homogeneous, smooth distribution. It could be very noisy, so to say. Let's compare that to, so this is a quantum particle, but we know that interference is not necessarily a quantum effect, right? Also waves in classical physics, we know about waves for hundreds of years now, they can also interfere. And we can think about a similar experiment where we take a laser beam and we shine it through a scattering medium. And now from the Huygens principle, each time a laser can hit a scattering center, it will, from Huygens principle, for example, it will generate secondary waves. And again, the secondary wave hits another scattering medium, and that will also generate a scattering wave. And all these waves interfere. And again, when we look at the output, and now since we're talking about wave, our measurement is not counting ball, it's measuring the intensity, the power flow through some plane. We'll also get regions with constructive interference and destructive interference. And again, the intensity we'll measure will look grainy, will look noisy. And now we want to talk, so we know classically light behaves like a wave. We know quantum mechanically that if we lower the power of our wave, our laser beam, eventually we'll get to the quantum regime where we'll start seeing that the light is made out of photons. So we'll be, as we lower the power of the laser beam, we'll see more and more, we'll go into the rhythm of a quantum particle of photons, but still at the end of the day, we'll measure a very similar thing, because measuring the intensity, which is coming from the pointing vector, the flow of energy is equivalent of measuring number of quantas, number of photons in each cell. And therefore, it might be that as we lower the intensity of a laser beam, we'll start seeing the light arriving to our detector at quantas one by one, but the average distribution, the average number of photons or particles that we measure when we repeat the experiment again and again will follow exactly the same pattern as the classical intensity we would expect from a coherent laser beam. By the way, I didn't mention this at the beginning, but please feel free to stop me at any point, either by opening your mic or writing a question in the chat box, and I'll be happy to answer a question, which I potentially try to give a broad introduction so it will be accessible to a broad audience, but please feel free to stop me at any point if you have any questions. So this duality between a wave and a particle description of light is actually quite more fundamental than this specific example of scattering. And in fact, every time in any experiment where we measure just the mean photon number, when we just count how many photons arrive to each position, which is equivalent to measure the intensity, the optical intensity, these kinds of experiments cannot distinguish between the classical and the quantum theories of light. Okay, and what do I mean by classical and quantum theories? Classical theory of light is just Maxwell equation. I described the light as electromagnetic fields that obey the Maxwell equation. Quantum theory requires us to take these fields and do second quantization to turn the complex fields into operators, usually the creation and the annihilation operators of a photon, and then define a number of operators that count how many photons we have in different positions and so on, and start developing the quantum theory. So any experiment that just counts how many photons I had cannot distinguish between the classical and quantum theory. So how do we distinguish? And this whole talk, this whole field that I'm involved in is dealing with the quantum signatures of light. For that, for these kinds of experiments, we need to take usually two detectors, two single photon detectors. So each one of these is a single photon detector that can tell me if a photon arrived, if it detected a photon or not. And I need to take two of these and do what we call a coincidence count, a coincidence measurement. We do a cross correlation between the signal coming from one detector and the other, and look for events where when two photons arrive to two detectors simultaneously. And it's with these coincidence measurement, that we can start seeing quantum interference effect. And let me give you a simple example, and perhaps the most simple example would be, instead of this complex scattering that we'll talk about in a few minutes, let's talk about what happens when a single photon, a Fock state with exactly one photon, enters a beam splitter. Okay, so we have one quantum of light entering a beam splitter, and now, since it's a beam splitter, if it was a classical wave, half of it would be reflected, half of it would be transmitted, and we'll get half of the light on each detector. But this is a photon, it's a quantum that cannot split. So it needs to decide, does it reflect or does it transmit? But if I just count how many photons arrive to, I do the experiment again and again, many times, each time send a photon, and I just count how many photons arrive to each port, I discover that half of the times it derives to port number 1, and half of the times it arrives to port number 2. And that, again, it would distinguish me from just having a classical wave splitting into two. How do I see that my input was exactly one photon? I will look for correlations between these two detectors. Again, correlation or coincidence events where both detectors detect a photon simultaneously. So this is represented by this operator. It's the number operator in port 1 times the number operator in port 2. And now I see that since I started with a single photon, this correlation will always be 0 because the photon is either here or there. It will never be, if it's a single photon, it will never be at both ports simultaneously. And again, if we think of photons and balls as balls, this is quite intuitively, right? It's either here or there. And it's a way to distinguish from a wave that can split. It can be half here, halfway. A wave can do that, a single photon can't. So this, I think, is quite intuitive and gives a flavor of why we look for correlation. And this is, by the way, called by Hanbury, Brown, and Twist after their novel innovative experiments in the 50s of the last century. But there's even a more advanced version of this, which is I find much very surprising, and it's the Hongao-Mandel effect, where instead of having one photon entering the beam splitter, we have now two photons entering the beam splitter, one photon from each port. And again, we do the same kind of measurement. We have two single photon detectors. We ask how many photons arrive to this detector and how many photons arrive to the other detector. And if we just look on the average number of photons, we started with 2 photons, half of them went here, half of them went there. That means that on average, we'll measure 1 photon on detector 1 and 1 photon at detector 2. This is not too surprising, but what we discovered that even in this case, when we have, or not we discovered, Hongao and Mandel discovered in the 80s, even in this case, when we have 2 photons entering, they will never end 1 photon in one port and the other photon in the other port. This coincidence measurement, its correlation will always be 0. And this is already a true quantum interference effect. And the way to understand it is by looking at all the 4 probabilities that we have. I have 1 photon coming from this port, 1 photon comes from this port. Either one is reflected and the other is transmitted, and both of them end up at this port, or one is transmitted and the other is reflected, and both of them end up at this port. But we're not looking for these kinds of events. We're looking for events, these coincidence events when one photon is at port 2, the other photon is at port 1. For these kinds of events, there are 2 possibilities that can lead me there. Either both photons are reflected or both photons are transmitted. So we have to, when in quantum mechanics, when we have 2 paths that leads to the same final state, we have to interfere them. We have to take a coherent superposition of them. And it turns out that for a beam splitter, a unitary beam splitter, there's a pi shift between this option and this option, and therefore we have a destructive interference and a zero net probability for this to happen. So for this process to happen. So this is an example where these kind of coincidence measurements can really reveal a quantum interference effect. And this is for a simple case of two photons hitting a beam splitter. And we want to take this one step further and more generally come with two photons to some complex medium as the one in the examples I gave in the first slide. And now each one of these, there are many trajectories that each one of these photons can take into the sample. And I described it here mathematically, this sample as with a scattering matrix, a matrix that tells me that given I entered port number A to the in this system, what is the probability, what is the amplitude to get at the output at port B? And again, I can use this formalism to compute these coincidence maps, these correlations, and look for quantum interference signatures. So this is all the measurements that I'm going to describe today, and most of the measurements done in this field of quantum light in complex medium can be mapped to these kinds of measurements. You have multiple inputs, multiple outputs, you put two detectors at the output, and you look for coincidence maps between them. And kind of we look for generalizations of these Honga-Mandel interference effects from the previous slide. So before describing these kind of experiments, let's take one step back for a second and talk about scattering of classical light. Because we're looking for, it's a motivation, at least my motivation to look for these quantum effects in scattering medium is that we know from the classical theory of light that even though coherent light scatters in random medium, there's some, and interference is usually a very sensitive effect. There are some robust coherent effects that are very robust and can survive disorder averaging. And we're looking for these kinds of events because if you could find quantum coherent effects that survive disorder averaging, that could be really interesting both on the fundamental level, but also for applications that maybe I'll mention a little bit later. So here's a classical coherent effect. Again, classical light, everything I'm going to describe on this slide can be described by Maxwell equation and electromagnetic field. And here's the experiment I want to describe. Imagine here's my scattering medium. I illuminate it with a plane wave, coherent plane wave. Basically, take a laser pointer and shine on the wall in front of you, on a white wall, which can be modeled by these scatterers. So again, light can penetrate in, go inside, and then back. Some of the light will be transmitted to the other side. But if the scattering medium is thick enough, most of the light will backscatter, will go back to the direction we came in from. And if I take a picture, an intensity image of the backscattered light, I will see these speckle patterns, the patterns I described earlier, because they're at each point, at each pixel on my camera, light is coming from all the scatterers inside my sample, and so this light can interfere constructively and destructively. So in one pixel, it will interfere constructively, in another pixel, it will interfere destructively, and therefore I get these speckle patterns, these grainy patterns. And if you want to do this experiment yourself, just shine your laser pointer on the screen in front of you or on a piece of paper, and you'll immediately see these grainy patterns. And these grainy patterns are very, very sensitive. If you move a little bit your paper, as I do here in this cartoon, I move the scatterers, I see that any tiny movement of the scatterers will completely change the speckle pattern, okay? And now I want to take do a disorder averaging. I want to take a sum, an incoherent sum of all these images. Okay, I have many different speckled images. Now, and I sum all of them naively because for each movement of the scatterer, the speckle changes, the pattern changes, I would expect that on average, we'll see a homogeneous distribution of the intensity, that all these speckle patterns will wash out. And then I'll see on average something quite smooth and homogeneous. But in fact, when people have done this experiment back in the 80s, they've seen that you don't get a homogeneous distribution. Actually, you get a background, a more or less constant background, but a strong peak at the center. And they call this peak a coherent backscattering. So if I draw a cross section along this line, we really see we have some background, and on top of it, a peak. The peak is 2 times higher than the background, and its width depends on the wavelength. It scales like the wavelength, the optical wavelength over the transport mean free path. It was very interesting phenomenon. It's called coherent backscattering, and it was very exciting for these people because, for one, it's a coherent effect, and as I'll show you in the next slide. And for another, since it depends on the mean free path of the sample, it became a very sensitive way to measure, to characterize scattering samples. The wider this peak, the shorter the transport mean free path. And people are actually using this now to characterize scattering medium. Now, why am I saying that this is a coherent effect? Because if you walk through the theory, and again, the classical theory of light, in this kind of sample, you see that this enhanced peak at the backscattering, at the center of the backscattering pattern, results from interference of time reversed paths, of reciprocal paths. What do I mean? Imagine this plane wave impinging on my scattering medium. And now let's pictorially think of the light can go in many different trajectories inside the sample, but for every trajectory it can go, for example, the trajectory I drew here in yellow or orange, there's a time reverse trajectory that can go through the exact same scattering centers. And since it goes through exactly the same scattering centers, it will accumulate exactly the same phase. And if it accumulates the same phase, it will interfere constructively. So therefore, I have a coherent interference effect, a constructive interference effect between these time reverse paths, and which leads to this enhanced intensity exactly at the backscattering angle. And why is it exactly at the backscattering pattern, exactly at the center? Because if I would look not at the same angle so this is the angle I illuminate with, if I look at scattered light at some other angles, I'm not guaranteed to have these time reverse paths. And that's why I have a strong peak at the center and some homogeneous background around it. Now, what's nice about this peak is it's very robust, because to break time reversal symmetry in optics is very, very difficult. You need some strong nonlinear effect or some strong magneto-optical effect, but otherwise, most of the samples we know don't break time reversal symmetry. So it happens almost in any scattering medium that you will try. And it's also very broadband, even though it's an interference effect. It is insensitive to the wavelength of the light. You can come with a really white light and you will see this peak at the center, unlike most of the interference effects we know that are very sensitive to wavelength. And this is why it was a very exciting effect, and we want to see its classical counterpart in quantum optics, for quantum light. Okay, so again, we want to send a quantum state of light, something that cannot be described by Maxwell equation, shine it on a scattered medium, look at the backscattered light, and see if we have interference effect. So this is our goal. And now I want to say a few words on what do I mean by a quantum state of light, or how do we generate, and I'll say that since I'm an experimentalist, instead of writing equations, I'll explain how we generate this state in the lab. So what we do is we take a nonlinear crystal, and nonlinear crystal means that if we focus through it, a strong blue laser, that we call a pump laser, because of the nonlinear interaction, a pump photon can spontaneously split into 2 daughter photons that we call signal and hydra. Now I say spontaneously because most of the blue photons will just pass through the crystal and will not split, but some of them, a small fraction, will split, and we're filtering out only those photons that split, and their frequency will be in the near infrared, or because we started photons at 400 nanometers, and because of energy conservation, the sum of the frequencies of the new photons has to be equal to the frequency of the pump photon. So I need this process to conserve energy, and this process also conserves momentum. And that momentum conservation, which in the jargon of nonlinear optics is often called phase matching, guarantees that, or I can tweak the parameters of the crystal such that I have photons emitted from the crystal at many different angles. Okay, so I have a large uncertainty at which angles they will come up out of the crystal. Okay, this is depicted here in the arrows going to many different directions. But these photons are entangled, and they're because of momentum conservation. What does that mean? That if I know that my signal photon went to the right at some angle theta, the either photon, its twin photon, has to go to exactly the opposite angle at angle minus theta. Okay, so the sum of their k vectors will always be equal to the sum of the pump of the k vector of the pump. And mathematically, we write this as a superposition state, as a superposition of photons with different transverse momentum. Q here represents transverse momentum, which is exactly the angles I mentioned. Okay, so at the output of the crystal, this is the state I have. It's in a superposition. I don't know at which angle or what is the transverse angle of transverse momentum of each photon, but I know they're always anti-correlating. How do I see this in the lab? I take a single photon detector, I place it at the far field of my crystal. I do this with the lens and working the focal plane. And first, I just take a single photon detector and I scan its position along the Fourier plane, the far field of the crystal. And I count how many photons arrive to each pixel. And I see a very broad distribution. This is because, as I said, I don't know at which angle these photons were emitted. But this is kind of boring. It doesn't reveal to me anything about entanglement and correlation. In order to see correlation, and as I mentioned in the introduction, to see quantum features, I have to take two detectors. So here are my two detectors. One of them is static. I fix it in its place. The photons are in the Fourier plane, the far field of the crystal. And the other detector is, I'm scanning its transverse position in the Fourier plane. And I look again for these coincidence events. What are the chances? What is the probability that I detect simultaneously a photon on this detector and a photon on the other detector? And what I see now that is, unlike the broad distribution I had before, now these photons are tightly correlated. If I found a photon in this position, I know exactly where its twin photon will be. Now, this is correlations. This is not enough to show that these photons are entangled. To show entanglement, I need to repeat this measurement at the near field of the crystal. I need to move the detectors to the plane of the crystal, right outside, image the photons right outside of the image and out of the crystal. And I see that also here they're tightly correlated. If I know the position of one photon at the near field, I know the position of the other photon. And actually, one can certify entanglement and show that this state coming out of the nonlinear crystal is entangled by measuring the width of the distribution in the near field and the width of the distribution in the far field. And if the product of these distributions is smaller than half when I measure in the right units, then I can certify that I started with an entangled state. So there was no scattering so far. Now I'm going to add the complex medium, the scattering, some thin scattering layer, and I place it right after the crystal. And we're asking what will happen now. Let me first mention that in optical frequencies, scattering is a unitary process or elastic. In optical frequencies, most of the scattering is elastic scattering, so coherence is not lost. It just scrambles things, so I take this scattering layer, I repeat the measurement I described in the previous slide. First, I just measure the mean photon number, the number of photons at each position, and I don't see anything interesting. It's the same broad distribution I saw before. But now when I do the coincidence measurement, that before gave me a very localized correlation at the center, now instead of a localized coincidence map at the center, I see what we call two photon speckle. And it's not it's like the classical speckle I showed you before for a laser beam, but now it's a speckle in the coincidence map, in the correlation between two single photon detectors. And I said, we call it two photon speckle. We, in the royal we of people in our community, actually, the first team who realized this was the team by Van Exter about 15 years ago. And they saw these speckle patterns in the coincidence map carry a lot of information. They realized that even though the entangled state was scattered, it carries a lot of information on the quantum state of the photons. And they actually were able to show that if we look at the single counts, again, the mean photon number, how many photons I have in each pixel, and measure the variance of this or the contrast of this pattern. And if I look at the coincidence map at these speckles and measure the variance of this pattern, then one can show that these two quantities can tell you, for example, what is the purity of the sample. For example, if you have a strong fluctuations in the coincidence maps or a variance that equals to 1 and no fluctuation in the single counts, a variance that equals to 0, then you know that your state is pure, that the trace of the density metric square equals 1. So this was a very nice understanding of them, how to extract information on the quantum state from the two-photon speckle. They've also showed that from the contrast of the coincidence map, you can find the Schmidt number. The Schmidt number is the number of states in the superposition of the two-photon state, of the entangled state. So there's a lot, and just like in classical optics, there's a lot of information that is carried by these speckle patterns. But the thing is that also, like in the classical case, these speckle patterns are very sensitive to interference. So if I slightly move the scattering sample, I would expect that these two-photon speckle will be disappeared, and this information will be lost. So actually, this is what we tried to look more deeply into. We wanted to see both in the, so for classical light, again, I showed you that we get speckle pattern. If I do disorder averaging, if my sample moves around, then on average, I get a homogeneous distribution. In the transmission, when I look at transmission, this part I didn't show you, but I showed it for the reflection. If I do disorder averaging, I no longer get a homogeneous, a flat distribution. I get a strong peak at the center because of this interference of time reverse path. And what we wanted to see is whether we have a similar effect in the quantum regime. So first, let me start with describing the experiment in the transmission. So it's the same experiment I described before. I have a nonlinear crystal generating pairs of entangled photons. They go through my diffuser, and I measure the correlations, the coincidences between two detectors at the far field of the scattering medium. And first, it's exactly the same experiment before. It's just one-dimensional now. I look for the correlations. Here we write them as G2, but it's the same type of correlation between detectors I described before as a function of the distance between the detectors. And I see this grainy, this noisy pattern, this fluctuation, this two-photon speckle. And now the new part in this experiment is that now I rotate the diffuser and I do a disorder averaging over this speckle pattern. And again, from classical light, we would expect, because this is a transmission geometry and I don't have time reverse paths, for classical light, I would expect to get a flat distribution, that all these speckles will wash out and the average distribution will be flat, will be constantly one when I normalize by the average intensity, an average number of photons. But what we found, and it's that it's not homogeneous. There's actually a peak. So similar to the coherent backscattering effect, we saw that at the center, but there's 2 times probability to get a coincidence map than on the background, and that happens even when you do disorder averaging. So the diffuser, the scattering medium keeps rotating, keeps moving, and this is what we see on average. And in fact, we're not the first to see this. Again, of an expert team have seen it before, but what we have recently showed, and when I say we, it's actually my wonderful students, and in this case, Awad Leib, who realized that it's not only that and the disorder averaging is not flat, it also carries some information on the entangled state we had before the disorder averaging. And he was able to prove that this peak, this region with enhanced correlation, is wider than what we would have expected from a width of a single speckle grain. The width of a single speckle grain scales like the wavelength over the size of the sample. But what Oad showed is that the width of this enhanced correlation scales like the wavelength over the correlation of the photons, how tightly correlated they are in the near field of the crystal. And this is exactly the same width that people use to characterize entanglement between photon pairs. So in fact, we were able to show that because this width of the peak is wider than the width of a speckle pattern, out of speckle grain, we could show that, that these photons were in an entangled state. And for us, it was very surprising that we could certify entanglement, even though the photons went through a scattering medium that moved all changing time and smeared or seemingly smeared the correlation, but in practice we see that it didn't smear all the information. We could still certify entanglement. So this is very nice. We saw that in the transmission disorder averaging, there's still some coherent effects that survive disorder averaging. But what we found that unlike the classical coherent backscattering effect, this region of enhanced scattering is basically a narrow band effect. So if my photons are not exactly their frequency, remember I told you their frequency is half the frequency of the pump photon that generated them. But if I could tweak the phase matching so that their frequency will be broader than that there'll be some uncertainty in their frequency, that the frequency will be broadband. And in that case, this effect does not survive, it's smeared. And we wanted to see if there, which is in contrast to what we see in classical coherent backscattering. So we wanted to see what happens if we look at the reflection at the backscattering geometry, can we recover this broadband feature of classical light, of backscattering of classical light? So this is the next experiment I want to describe. And this experiment was run by another fabulous student, Mamoun Sapadi, who ran this experiment. And it's similar to what we had before, a nonlinear crystal generating pairs of entangled photons. But now we take our two detectors. Okay, the entangled photons illuminate the scattering medium, they backscatter, and we collect them with two single photon detectors, and we look for coincidence events where both photons, both detectors detected the photons simultaneously. Okay, so again, before we look for the coincidence, we just looked at the single counts, the mean photon number. How many? Okay, this is an illustration of my experiment. I have I don't show here the nonlinear crystal that generates the entangled photons. They go to the beam splitter. Half of them continue to this port, but we discard those photons. Half of them go to the scattering sample. They backscatter through the beam splitter, and then they split on the second beam splitter here. One of them goes to one detector, the other goes to the other detector. And first, we just discard the photons that go to this detector, and we just look at the single counts. How many photons arrive to each position of the detector? We scan the transverse plane, and we don't see anything. We can't see a homogeneous distribution. Again, this is a feature that when we look at the average photon number at different positions, there's no information there. But now we do the coincidence. We have another detector, and we look for their correlation. And when we do that, we discover a peak at the center of the distribution. And so here's the two-dimensional map, and if we take a cross-section, we again see a background, and on top of the background, a strong peak, and very similar to the classical case. So we're very excited. Again, it's a coherent effect that survives disorder averaging, because also here, we do disorder averaging. The sample is on a rotating diffuser. The team's spinning while we do this measurement, and this measurement is very long. Actually, it's a few days to take this data. But after we do all this averaging, we see the peak on top of the background. And next, we wanted to compare this peak. Okay, so again, of the quantum case, the case where we shine two photons on the scattering sample. So again, average mean photon number, the single counts don't show any feature. The coincidence count, the correlation, see this peak. And we wanted to compare this quantum case to the classical experiment. So we did exactly the same with exactly the same sample, the classical experiment, and look at the intensity or the mean photon number. And we also see the classical coherent backscattering effect. But what you can notice is that the width of the peak is wider in the classical case than in the quantum case. And if you remember, I mentioned at the beginning of the talk that the width of the peak tells us something, gives us information on the transport mean free path of the sample. So we want to look deeper into this issue of the deep, and why is the quantum case, the peak at the quantum case is more narrow. So we talked to our excellent collaborators, Wade Hassou from University of Southern California and Arthur Gucci from Institute of Langevin in Paris, who did numerical simulations and analytical calculations, because it's quite complicated to deal with all these quantum trajectories in these scattering samples. But together with them, we understood that this is not some experimental artifact. Indeed, the quantum peak is more narrow than the classical one. And in fact, we could show that the quantum peak, this is the numerical simulations, is these green diamonds here, is exactly, its shape is exactly the shape of the classical peak, which is the blue open circles here, squared. So if I square the classical peak, I get a more narrow peak, and this is the quantum peak that I get. And this means that the slope here, the slope of the peak cross to the center, is in the quantum case, the slope is 2 times larger for the quantum case than the classical case. And it means, if you remember, I mentioned that the width scales like the wavelength over the transport mean free path. In the quantum case, it means that the wave scales as half the wavelength over the transport mean free path. And this was exciting for us because there's a lot of quantum effects where the 2 photons together in an entangled state behaves like 1 photon at half the frequency. This is half the wavelength. This is quite known, but what's exciting here is that this effect survives disorder averaging, which was, at least for me, was new and exciting. And it's also exciting from the application perspective, because then we said, okay, if the slope is larger, so the width of the peak is more narrow, does it mean that I can estimate the width of this peak? Can I give a better estimation of the width in the quantum case than in the classical case? Because usually when things are sharper or more narrow, we can estimate them better. Now I say usually because the question whether a narrower cone or a more narrow peak gives me a higher precision is not a question of just about the shape, but as is often happened in quantum metrology or in general in measurement, the sensitivity also depends on the noise of the measurement. And in our case, there are 2 contributions to the noise in the measurement. One contribution is shock noise, is the fact that at the end, we're collecting discrete event of detection of photons. And every process that involves discrete detection event has some shock noise, and the noise there scales as the square root of the number of photons we detected. Another source of noise is speckle noise. And speckle noise results because we started with a speckle pattern, right, for a single realization before I did disorder averaging. And then we brought it in the diffuser and average. But if I didn't average over enough disorder realization, I will have some leftovers from this speckle pattern. And this is the speckle noise that scales like the square root of the number of disorder realizations I had. Now, we computed to see what's the fundamental limit on the sensitivity of measuring the transport mean free path from the width of the speckle pattern. And we could compute that by computing the Fisher information that depends on our noise sources. And 1 over the Fisher information gives us a lower bound on the variance of the estimator of this transport mean free path. And what we found is when we're in the regime where the number of photons is much larger than the number of realizations. And this can be when in the regime when my sample is static, it's not moving, and I can take the integration times as long as I want. So it probably won't be relevant for biological tissue, but for some nanophotonic devices, things that are static, you could basically shine your light and collect the photons for as long as you want. And for these cases, when you collected enough photons, one can show that the quantum estimator of the transport mean free path is 4 times, the variance in the estimator is 4 times lower, which means my measurement is 4 times more sensitive in the quantum case than in the classical case. So again, this was new for us and exciting because it's an example where quantum sensitivity helps, even though you had scattering and disorder averaging. And these are things that usually intuitively we think kill quantum advantages. But here we see some kind of advantage, again, in a niche, in a very precise, specific application, but it's a nice application where things survive. Okay, so in the last 10 minutes or so I've got left, I want to a little bit shift gears. And up to now, I talked about more fundamental properties. And now I want to do more about towards applications. And there's a lot of activity on that, especially thanks to this really incredible device called a spatial light modulator. A spatial light modulator is a matrix of liquid crystal cells. Basically, all the liquid crystal displays, the LCD screens that we are all looking at now on our laptops or computers, they are also made of matrix of liquid crystal cells. And these liquid crystals can change the phase of the light that propagates through each one of these pixels. So we can address these pixels electronically, and by that really tailor the phase. It's an optical element that when light passes through it or reflects from it, it can accumulate a phase that we precisely tailor. And this incredible device is very, very helpful for overcoming scattering of light. And here's a beautiful example, or actually not an example, it's a work from 15 years ago from Alan Mosk and Ivo Velikov, who really made a paradigm shift in our study and application of light, of classical light in the meantime, in scattering medium. So what Alan and Ivo realized is that you can take these spatial light modulators and tailor the optical wavefront such that after the scattering medium, even though you had lots of scattering, you can look for the spatial light, the pattern you need to put on the spatial light modulator, so that after the scattering medium, you have a spherical beam focusing to a spot to a pixel on your camera. And how do you find this wavefront correction? Well, there are many ways, but the simplest one is you just look at the intensity that you want to enhance, and just do a feedback loop. You try to iteratively look for the correction that will focus your light onto a single pixel. So again, this was done and is used today a lot in classical light. And in recent years, following the new work of Sylvain Gigan in LKV in Paris, people are using this also for quantum light. So for quantum light, the problem is that the feedback is very, very weak. And we need this feedback in order to find the correction, the SLN correction, in order to enhance the signal. So what they do often is take a bright laser beam and that is at the same wavelength and the same polarization as your single photons. First, let them go through the exact same scattering medium and exactly the same angle as the angle that the quantum light is going to pass through. And find a correction for the classical beam, then quickly switch between the quantum source and the classical source and the quantum source. And if you did it fast enough and nothing moved, then the same enhancement that worked for the classical light also worked for the quantum light. And there are many different works along this avenue. We did something slightly different. We showed that we could put the spatial light modulator on the pump beam, on the blue photon, the blue laser that generates the entangled photons. And instead of doing the correction on the entangled photons, we pre-designed the photons before they were even born by doing the optimization on the pump beam and in that way, we were able to show that we could take the two photon coincidence map and that was before the optimization speckle and focus it to a spot.
Professor Yaron, about
yes.
10 minutes to conclude, and then we'll take questions for 5 minutes.
Excellent, thank you. I have just a couple of more slides, and then we'll have a more time for questions. So thanks for the note. Okay, so really these are my last few slides where I want to flash a little bit about more applications, and these are not applications from my lab. This is just applications for other very active in groups in this field. And this work is coming actually from the quantum communication community, the work of Shenwei Pan from China, where they're working a lot on quantum key distribution in free space. And here is Alice and Bob and Charlie in the middle, distributing entangled photon pairs 20 kilometers apart from each other. So they have here a station inside the city with all the turbulence and all the problems of doing a quantum experiment in real life scenario. And you know, the turbulence in the air distorts the wavefront and really limits the collection efficiency at Alice and Bob's side. So what they have here is a beacon laser. So Bob sends a classical laser to Charlie. Charlie measures with a wavefront sensor the distortion in the wavefront, and found these distortions and a spatial light modulator or deformable mirror. He understands what kind of compensation he needs to put on the single photon that he generates that and sends back to Bob. And Charlie does the same thing with Alice, and this way they were able to enhance the distance between Alice and Bob to 20 kilometers, thanks to this adaptive optics or wavefront correction optimization. So this is a very nice demonstration of how, with wavefront shaping, you can overcome the effect of scattering of single photons and entangled photons. Another beautiful example comes from Maul Malik's lab at Heriot-Watt University. They wanted to distribute entangled photons through a multimode fiber. So, and these are high-dimensional entanglement. High-dimensional means that the photon can be in one out of, in this example, 7 different pixels. And they want to do entanglement over those 7 pixels. And when you, just like what I mentioned in our experiments, when we want to show entanglement, we need to do near field and far field measurements. We have to do measurement in 2 different bases. We call this in mutually unbiased bases. So here, to show entanglement between several pixels, you need an SLM at the Alice and Bob's end and kind of mix all the pixels with one to each other. But they also want to distribute, they have a source of this high dimensional entanglement, and they want to distribute it between Alice and Bob that are far away from each other. And they want to do it because these are high dimensional entanglement, then you need several pixels, you cannot distribute it with a single mode fiber, you need a multimode fiber. But the multimode fiber scrambles the entanglement and generates speckles in the same way that we discussed so far. So what they show that by first characterizing the fiber and then using the spatial light modulator to apply a correction, they were able to take this scrambled state between Alice and Bob and show that it's entanglement both in by measuring strong correlations between Alice and Bob, both in the pixel bases and in this mutually unbiased bases. And this is, again, very exciting that you can distribute entanglement through this scattering or complex medium, which in this case is the multimode fiber. And the multimode fiber is complex because, you know, in real fibers, the modes are always coupled. If the fiber is long enough, then every twist and bend and so on couples between modes, and that acts like scattering. Finally, and this is really almost my last slide, I want to just mention that complex light, what I talked so far on applications, the scattering was a bug, right? It was something annoying that we tried to overcome with wavefront shaping. What Alan Moskin and Pipen Ping showed from Twente, from the University of Twente, they showed that sometimes scattering can help you. And in this beautiful example, they used the scattering for key authentication. So suppose what they are recommending, you take a small scattering medium, a white paint, and put it on your credit card, and you go to the bank, and the bank wants to see that this credit card is authentic, it wasn't fraud. So the bank knows what kind of shape of light with how you need to structure the light and illuminate this key, your credit card, in order to, when it's back reflected, to get all the light focused to a spot. Because the bank generated this key, but this key, it's a white piece of, it's a white drop of paint. It's very complex. It's very difficult to replicate, or practically impossible. So if you come with the wrong scattering medium, you get the speckles, and then the bank will know that its wavefront correction will not match the key, and therefore this credit card was fraud. And they use here, they use here states of light with a few photons, because they show that if you just have a few photons in this light, then you can guarantee quantum mechanically that this thing cannot fraud. And here I'm really ending with my take-home message of why am I excited, and this community is excited with quantum light and complex medium. For once, it's because there's a lot of things happening with classical light, like wavefront shaping and understanding of these robust coherent effects that survive this order averaging. And it's interesting to think of their quantum counterpart. And from the other side, there's a lot of interesting and new applications like quantum key distribution. And it's now interesting to revisit all the knowledge of classical light of scattering of classical light and see how we can utilize it for quantum applications. And I end by thanking my wonderful team of students and my collaborators, Arthur Gucci and Wade Hasu, and of course the funding agencies. And I want to thank you for your attention. And I'll be happy to answer questions. And if you have more questions, then you could also visit our website and take a closer look at this review article, which I try to follow in this talk. So thank you very much for your attention.
Thank you, Professor Yaron. This was a wonderful talk. And the best part is that there are many students and you already have a review talk, so they can. So actually, before, at the end of the last talk, they were asking that whether there is a material means which they can follow. And here is answer for the second.
Yes, exactly.
Neat material which you can follow. So now the floor is open for questions. Please ask. I mean, you can type in chat, you can unmute yourself or ask questions.
So yeah, I have a question.
Please continue.
So like in the coherent backscattering case, the incident beam of light, was it coherent? Completely coherent? Like my question is, like, if we use a partially coherent beam and we expect the scattered light to be partially coherent, would that bring a lot of reduction in speckles formation? Because
Yes, thank you for the question. Excellent question. So do you have a follow-up? No?
sorry, can you please repeat?
Yeah. Are you asking about the classical coherent backscattering effect, about this?
Yeah, I'm asking about this like we send a coherent light. When it hits the sample, it scatters back. So instead of sending a coherent light, if we send a partially coherent light, would that help in reducing the speckle formation?
Okay, excellent question. So I should divide my answer to two, and let's talk about temporal coherence and spatial coherence. Okay, so
Okay.
if we're talking about temporal coherence, so let's imagine I take some source, I pass it through a single mode fiber to make sure, or some spatial filter to make sure I have a single spatial mode. And this single spatial mode is a plane wave. But I don't have temporal coherence, so its bandwidth is very wide. It could be white light. Okay, take a light from the sun, couple it to a single mode fiber, and then collimate it at the output. Okay, so very broad spectrum, but still a plane wave after I collimated it, or nearly a plane wave. In this case, I will see coherent backscattering. And as you mentioned, what the incoherence or partial coherence will do, it will reduce the contrast of these speckle patterns. It will smear these speckle patterns, but that's actually good for me because it will mean I need less disorder averaging. You remember, to get this peak, I had to move the sample many times and look at the average intensity. If I have partial coherence, I get that for free. I smear the speckles, but the peak will not disappear. This is for temporal coherence. If I have spatial incoherence or partial coherence, which means I cannot think of my light as a plane wave, or I need to think about it as an incoherent superposition of many plane waves, light coming at many different directions, or if you want, light that is not collimated, it diverges. This will smear my coherent backscattering peak. If I'm, the more modes I have in this spatial incoherent source, the narrower will be the peak. And one way to think about it is that even for a spatially incoherent source, I can decompose it. I can think of it as a superposition of light in multiple multiple different plane waves. Each one of these plane waves will generate a coherent backscattering peak, but at a different location. So now I need to take a incoherent sum of all these peaks because it's an incoherent source. So many peaks at different locations will give me again a flat distribution. So this is a convenient way of thinking why spatial incoherence smears coherent backscattering effect, but temporal incoherence doesn't smear it.
Yeah, thank
Does
you.
that answer the question?
Yeah, completely. Thank you.
Yeah. Thank you for the question.
Any other question? Anyone else? So, Rajit,
I have a question. Can I ask?
Please, continue.
Thank you for your talk. In case of SPDC, that is spontaneous parametric down conversion process, we have not only correlation between intensities of photons coming from two beams, but also noise is correlated. So my question is, can we extract information from noise correlations of photons from each beam and improve the output coincidence results? This is the first question.
That's an interesting question. I assume, okay, when you say noise, I assume you mean let me say, we work in the weak squeeze or in the regime where we only have a pair detection time. So it's a stream of pairs that come up every now and then. And in this regime, I think that we kind of have to work in this photon counting regime and coincidences. But you're right that if we can, if we increase and work, sometimes people work in the what's called bright squeezed vacuum, or so to say, where you could start talking about intensity correlations and phase noise, right? Because you have more and more pairs in coming out that you can describe this state in terms of squeezing. And I think that that's I would assume you get a similar effect in the coherent backscattering geometry. And probably you could gain information by doing phase correlation measurements. But I have to be honest, I haven't thought about it truly. This is an interesting question. If you have some thoughts about this, or if you would like to follow up later, then please feel free to write me an email and we can discuss this further.
Okay. Second question is, do you have any plans to use polarization degree of freedom of photons in studying complex media?
Yes, definitely. So polarization is a very important thing, and you know the nice thing about giving this more broad overview talk is that you can skip the nasty details and of the experiments. And one nasty detail I skipped is indeed polarization issues. So in these experiments I described, all the photons had the same polarization. And we took scattering medium that doesn't mix polarization. So in this type of experiment, it was type 0 for the experts. It was type 0 down conversion and no polarization. So things were simple. We're definitely, and we're working now on utilizing polarization effect, which makes the story much more rich and interesting, I think. And for to give a teaser, you may know that people are using polarization to mimic fermions with photons. And I know it sounds strange. How can you mimic fermions with photons? But if you use the polarization degree of freedom to generate an antisymmetric state, a singlet state, a photon is a boson. There's nothing you can do about it. But a boson means the entire state has to be symmetric. If the polarization part is antisymmetric, then the spatial part is also antisymmetric. So then we can mimic states in the spatial domains that are antisymmetric, and that behaves like fermions. And there's I believe, a lot of interesting features to look at fermions in this scattering medium. And some of these features were already started by the Nexter team. So yes, the short answer is yes, polarization is interesting, and we are definitely looking into that.
Thank you.
Thanks, Prof.
Any other question? Anyone else have any question? If not, let us thank both the speakers of this session. And once again, especially Yaron Bromberg for this excellent talk. And
Thank you.
now the technical part of the session is over, and I hand over it to the organizers if they have any announcement.
Yeah, thank you, Anwar, and thank you, Professor Bromberg. Excellent, very enjoyable session. Our team, do you have anything to announce today?
Yeah, thank you all. And we would like to announce that tomorrow's session will start from 10 a.m. till 1 p.m. Followed by there will be 3 sessions, and we would ask all the participants to join in large numbers. So yeah, that's it from our side. Thank you.
Thank you. Bye.